Hi guys, this is going to be a lecture video about ideal gas and kinetic theory. Alright, so we start with temperature. What is temperature? So far we basically say hot and cold. So hotness or coldness is basically represented, it's representing the temperature, or whatever the thermometer says. It's 20 degrees Celsius or 70 degrees Fahrenheit. So that's what temperature is, but in reality, in physics or in science, it's basically the how much energy molecules have in their system. So once you add energy to the system, then they basically speed up. So basically they have more energy, and that means they have higher temperature. We're going to dig more in detail to that later on. Alright, so thermometers, like we said, they are used to basically measure the temperature. And there are a lot of different thermometers, actually. You probably know just 3 of them, but there are a lot more than that. And these are basically some old thermometers, and they're in a museum in Italy. And the main idea of thermometer is basically using the idea of expansion. Because when you heat up something, they're basically expand. Or once you cool it down, they're going to shrink. So basically they use this idea to basically build a thermometer. And the common thermometers today consist of hollowed glasses tube filled with mercury or alcohol with different color. So once you basically heat it up, it basically rises up, and then you are able to basically see the temperature. And this calibration is basically made according to the properties of the liquid or the alcohol that you're using in the thermometers. Alright, so we basically have 3 scales that you guys know of. So Celsius, Fahrenheit, and Kelvin. But in this, on ramps, and some of the questions, actually there's one question, but I just wanted to add all of the others. So you also have 2 other measurement scales, and this is Rankine and Rameau, or something like that. This is a French word, I don't know how to say it. So basically these are different scales of thermometers, and they all have different references. So for example, for degrees Celsius, we basically take freezing point of water as 0 degrees Celsius and boiling point of water as 100 degrees Celsius. So they are basically the references. So they all have different references, and Kelvin and Rankine, so they basically have a reference of 0 degree, and this is basically the absolute zero, which is this like lowest temperature that you can ever calculate. And we will talk about it a little bit more in detail in a minute. Alright, so you have basically 5 different scales, and so far you probably have seen different equation for Celsius and Fahrenheit conversion, but this is basically putting all of the 5 different scales in one equation, basically. So all you have to do is, let's say you are trying to convert from Celsius to Kelvin. So you basically block out the other ones. You just use Celsius and Kelvin parts, and then you basically equal them. Or if you're using Fahrenheit to remove, then you basically use those two. Alright, so that's how you're going to use it, but this is the ultimate equation that you can actually have all of the conversion from any degree or any scale to any scale. So, and another thing over here, change of 1 degree Celsius. So if you change Celsius 1 degree, then what is going to be the effect in degree Celsius in Fahrenheit? So this is basically their scale, like how much they change from 0 degrees Celsius to 100 degrees Celsius. So this is obvious, it's just changing by 100. But Fahrenheit is changing by 180. So when this guy changes by 100, this is changing by 180. Kelvin is changing with the same scale, and Reaumur is changing with 80, and Rankine is changing basically 180. So that means if you change degrees Celsius by 1, then that means you're changing the Fahrenheit by 1.8. And every Celsius change is equal to the Kelvin because they basically increase with the same amount. But Reaumur is going to increase by 80, so that means 1 degree is going to be equal to 0.8, and Rankine is going to have the same scale as Fahrenheit, so it's going to be 1.8. All right, thermal expansion. So we said when we increase the temperature of materials, they're basically going to expand, or when we decrease the temperature, they're going to shrink. And there is a certain equation for that. So delta L is basically how much object is going to expand, or how much is going to change its length, and it depends on basically three things. It's basically depending on coefficient of linear expansion, and that is basically depending on the material that you have. Initial length, and how much temperature change. It's not initial and final. We don't care about the initial and final temperatures. We care about how much we change that. And it is basically measured in degrees Celsius. All right, area expansion. If you are basically talking about change in expanding in 2D, then you are basically going to increase the scale by you're just going to increase the scale. So for example, if you heat a thin circle ring in the oven, does the ring's hole gets larger or smaller? So you might think that it's just going to increase in size from inside, so it should actually get smaller. However, the way that it works, the area expansion is basically enlarging the entire thing. So it's just like you have a copy, and then you basically increase the scale it to, let's say, 200%. So once you increase the size to 200%, it basically enlarges in all of the sides. And as you can see, this inside circle is obviously larger than the smaller circle. So that means when you increase, the temperature is just going to increase in all direction. It is basically enlarging the object. And volume expansion, it is very similar to the linear expansion or length expansion. So this time we are going to look for how much volume is changing. And we are again going to need a constant, and it is coefficient of volume expansion and initial volume and how much temperature has changed. So basically this is how we find expansion of the volume. All right, thermal stress. So that's a little bit related with the expansion and Hooke's law, basically. So if the ends of a material is fixed, so we are basically trying to expand things, but if we are talking about, if you're blocking it, then it's not going to be able to actually expand. So what is it going to create? It's basically going to create some stress. So when temperature changes, compressive and tensile stress will be created on the material, which is called thermal stress. So thermal stress is basically the reason, or when you try to expand, it's not able to expand, and it is creating basically some force. So that is known as thermal stress. And since it's caused by the thermal change, it's called thermal stress. And the material is trying to expand, but the solid is in contact with the materials, exert a force to compress or expand. So to be able to keep the original length the same. So you are basically think that this is blocked from both sides. So once you increase the temperature of it, it's not going to be able to expand, and it's just going to create some force. So we are basically going to use the Hooke's law, or stress-strain relationship. So remember, force on an object, if you're trying to stretch or compress it, is going to basically depend on the Young modulus, the area, how much you extend or change the length of it, and the initial length of this guy, right? So, and this thermal stress is going to be actually calculated by force over area. So how much force you actually have in the cross-sectional area. So that is your thermal stress. So once you basically write this equation for F over A, then you basically have Y times delta L divided by L0. And if you also replace delta L in place, because delta L also has an equation, so alpha L0 times delta T, then L0s will cancel out. Then your thermal stress is going to be equal to basically yaw modulus times linear coefficient expansion and change in temperature. So depending on what is known, you can use either one of the equations. All right, ideal gas law. So this is something that you should remember from chemistry, or if you're remembering anything from chemistry, that should be this equation. All right, so basically, gases are going to have a certain relation or certain characteristics, and pressure and volume and temperature and the number of moles, basically they're going to have a certain relationship. So when you actually have, let's write some stuff over here. So once you actually change pressure of something, let's say you increase the pressure of a gas, then you will see that the temperature is also increasing. Or, and assuming that everything else is the same, so, or if you decrease the pressure, then you see that temperature is decreasing. Same thing, if you keep those guys the same, and if you increase the pressure, then you see that volume is decreasing with the same rate, or if you increase the pressure, volume is, if you decrease the pressure, the volume is increasing with the same rate. So, and again, if you keep pressure the same and change the volume and the effect on temperature, volume increases, temperature will also increase. If you decrease volume, then temperature will decrease. So basically, these are going to be the relationships, and they're all going to have their special names. To be honest, I don't know those names, but they're not really important. What important is this? That is the final, the ultimate equation that is combining all of those hopefully I'm going to be able to talk. So it's basically combining all of those variables. So P here is the pressure, and it's measured in Pascal. This is going to be basically the one of the most important thing that you guys need to be careful about. So equation itself, it's basically multiplying or dividing things, so it's not really difficult thing. But what you need to be careful is the units, because you can have a lot of different units for all of those variables. So make sure that you are using the correct units when you're making measurements. And V is your volume, and it's measured in meter cube, not liters. And N is basically the number of moles, and it's measured in moles. R is just a constant, and the unit for this is joule per mole times Kelvin. And T is basically the temperature, and it is measured in Kelvin, not in Fahrenheit, not in Celsius. All right, so this is known as ideal gas law. And for those gases, we actually have some assumptions that we are making because they're ideal. So it's not like any gas, theoretical technically, because most of the gases are not really obeying to this rule. But if everything was perfectly set up, nothing is lost in the system, no energy is lost in the system, then it would be acting ideal. So the assumptions that we are making in here are those. The number of particles in a system is huge, and the separation in between the particles is also huge. So when we are talking about gases, so that's what we also expect. The separation of gas in the particles is large. So this is number one assumption that we are making. And we are not expecting particles to go in certain directions. So we are assuming that they all move in the random directions. And this is important. The particles have perfectly elastic collisions. What does that mean? That means when they are basically colliding, they are not losing any energy. So elastic collision is actually the key thing in this assumptions. So no energy is lost actually when they are hitting the walls or hitting each other. And the other one is there are no forces of attraction between the particles of the gas, so they don't actually attract each other, and all particles are identical. All right, so these are some assumptions that we are making to say this is going to be the equation. All right, states of matter. So depending on the temperature, we are going to have different phases, and solid, liquid, gas, and plasma. So the number one difference in between those different phases is basically molecule distribution. So in solids, they're going to be pretty close. In liquids, they're going to be able to move like easily, but in gases, they are really far away from each other. So they are basically going to be able to fill in the room that they're in. And plasma is basically, it's a lot more energy that they have, and electrons and protons are actually separating from one another. So it's a different scale of energy that matter actually has. All right, so this relationship, solid, liquid, and gas, and temperature, so there is actually a relationship in between those. So when they are making analysis of the movement of the molecules, they are seeing that the temperature that we actually say, the temperature, is actually depending on one thing. This is depending on the kinetic energy of the materials. So you basically have a lot of molecules that are moving. So if you are able to calculate the kinetic energy, and what was kinetic energy? Remember, it is 1/2 mv square, right? So basically, mass and velocity of those individual particles, once you calculate every one of them and add them all together, then you are basically finding the temperature of the material. Or if you want to go backwards, if you are changing the temperature, then you are basically changing the kinetic energy of the system, which means mass is not changing, but kinetic energy is changing, so that means velocity of the particles is going to increase, so they're going to start to move faster and faster, and they're going to have higher kinetic energy. All right, so this is basically the relationship, and this Kb is a constant. It's a scientist name, Boltzmann constant, and it is basically measured in joules per Kelvin. So that means this temperature that we have in here is actually in Kelvin. And kinetic energy, it's a form of energy, so the unit for this is joules. So Boltzmann constant Kb is a very small number. It's basically this weird number. And another way of writing Kb, the Boltzmann constant, is actually coming from here. So number of moles and the gas constant, once you multiply those two and divide it by the number of molecules, then you are also able to find the Boltzmann constant. So here we basically have the average kinetic energy, but if you actually replace this Kb with an R over N, then that can also help you to find the total energy. So you just disregard the number of molecules. So your total kinetic energy is going to be 3 over 2 N R T. And you can also connect it with the ideal gas law. So remember PV equals nRT. So then you can just say K total is 3 over 2 times, instead of nRT, you just put PV. So this is also an option for us to use. All right, root mean square. So kinetic energy is temperature related, then temperature and average velocity relation can be written. So like I said over here, this is kinetic energy, and kinetic energy is basically 1/2 mv squared. So instead of K, if you just replace this 1/2 mv squared, so this line is basically representing the average. All right, so you're gonna see this term, so I just don't want you guys to get confused. It's not something different, it's just a name for the velocity in the system, but I'll show you why it gets that name. So this is the average kinetic energy, so I just replace it with 1/2 mv squared. Then mass is basically one thing, so there is no average for that, but velocity is going to have some average. So velocity square average. And then basically 1/2, those twos will cancel out, this m will come down, and then square of the velocity, and the average of that square is going to be equal to 3 kbt over m. And if you would like to find the velocity, then what do you need to do? You need to take the square root of your average of the velocity square. So average means mean value, right? Average. And since we are taking the root of it, it's basically root mean square. So since we are taking the root of the mean and the square of the velocity, then basically they have this name, root mean square, and it's shown by RMS. It's nothing special, it's just a name to describe this term right here. So VRMS is basically square root of 3 kbt over m. And average velocity of molecules is known as root mean square because it is the square root of mean of the square of the speed. All right, so, and this average VRMS is not the peak value. If you actually look at the velocity distribution of the molecules, it's just going to have random velocity distribution. Everything is not going to go at the same speed. So that's why we can't really say the speed of something, but we can actually calculate the average of it. And the VRMS is basically the average value of it, not the peak value. All right. Internal energy. What's internal energy? It is basically the total energy object has. And it is basically all forms of energy that we can have. So in materials, molecules are moving. So we are going to have some movement. So transitional kinetic energy. And objects are also rotating. So that's why we're going to have some rotational kinetic energy. And they also vibrate, so they also go back and forth. So they also have that vibrational energy. Plus, the last form is intermolecular energy associated with their bonding. So because of the bonding, they also have some energy putting them together. So all of those four forms of energy added together is going to be the total energy of the object. And it is basically known as internal energy. And internal energy is shown by capital U. And since it's energy, the unit is joules. And the internal energy of an ideal gas depends only on its temperature. So we're talking about energy of a gas. And remember, kinetic energy was related with temperature, so that internal energy of the particle as well. But it also depends on the number of molecules and the gas constant. And of course, the change in temperature, not just the temperature. So if you would like to change the internal energy of a substance, you definitely need to change the temperature of that system. All right, so that is it for basically ideal gas and kinetic energy theorem. So I will be solving the questions about this chapter as well. So please watch those videos, and that is going to help you. This lecture is going to help you to basically understand the questions in those in the question part. All right, see you in the next video.